Let's do a related rates problem. This such a big class of examples of calculus, and also just great ways to get yourself used to what derivatives mean and the chain rule and that kind of thing. So here's the idea for this one. We've got a helicopter illuminating some part of a neighborhood or like a field or something, maybe looking for somebody on the run that we want to find at night, and it's illuminating a circle down here. And the helicopter pilot notices that they think that circle's too small and they want to illuminate more stuff. And a simple way to do that is they're just going to go up, and that's going to increase the radius of that circle and also the area. So maybe they're doing that, and what we notice is we're looking at that circle and we see that the radius is increasing by 2 meters per second. We'd like to know how fast the area, the lit area, is increasing to get an idea of just how much coverage there is to find this person we're looking for. One thing I'm going to keep doing on this one and other related rates videos, I'm going to keep going back and forth between our specific example and a strategy sheet that I made up years ago. This is an elaboration of something you might find in Stewart's book or another book, a step-by-step procedure for doing related rates problems. I don't usually like step-by-step procedures, but I find that this is complicated enough that students really appreciate it. First step, draw a diagram. Well, we've got a diagram, but we actually, we probably want a simplified diagram, which would just be, let's say, here's the origin. This is going to be a top view of just this field or neighborhood or whatever, and there's the origin. Maybe that's right under the helicopter, and then it's just a circle, and then that radius is increasing. Maybe we could sort of denote that by some arrows going out like that. Okay. And we might even, sometimes you might even say, oh, and then pretty soon it will be a bigger circle. That could be definitely helpful. Okay. Next, and you don't it's not absolutely always something you can draw a picture of, but usually you can. Label the diagram with letters, variables. Don't label it with numbers. And that's unless it's something that's absolutely definitely a constant. So radius is something that's variable, so definitely needs to be a letter. And then, of course, we want the area A as well. So we'll call that big A for as usual. Okay, so now express the given information, the desired rate, in terms of derivatives, and look for increasing, decreasing. So let's go back. Okay, so R is the radius. A is the area. And we're given that dr dt is increasing by 2 meters per second. So that's plus. I'm going to emphasize the plus, even though we don't usually write that. Plus 2 meters per second. Make sure you're paying attention to the units. Okay, and we want dA dt. That's the rate we want to find. Okay, and this is a fairly simple example where there's really only going to be those three variables: the time, the radius, and the area. And in other ones, there might be even another variable. Okay, so the next step is really crucial. Write down a master equation relating the relevant quantities. And there's not more than two variables, so I get to skip all of this stuff. So we're going to write down a master equation, and then we're going to differentiate the master equation. So what does that mean? Okay, anything that relates the quantity that we're given the rate of change of and the quantity that we want the rate of change of. And of course, we know what that is. I guess I'll erase all this. In this case, that's pretty simple. A equals pi r squared. Now, in this case, the quantity that we want is actually already isolated on one side, and that makes it a little simpler, but that's definitely not super common and not necessary. So what we're going to do, we want to take this relationship that always relates any area to the radius of the corresponding circle, and we're going to differentiate both sides. These are really functions of time, and this is one of the things that can be a little weird. T does not appear explicitly anywhere here, and we're not differentiating by A or by R, we're differentiating by T, because we're in a situation where these are functions of time, even though this doesn't explicitly say that. But anytime you have two functions that are always known to be equal to each other, then you can differentiate both sides, and we get 2 pi r, and this is the mathematical key to it, which is because r is a function of t, even though it didn't say that explicitly here, This is really r squared is a function inside of a function. So when you take the derivative of r squared, which is really r of t all squared, you're going to get 2 times that, and then times the pi, the constant, times the derivative of what's inside. The chain rule will always come in here. The chain rule is absolutely crucial to all these problems. Okay, now this is really a good place to be, but it's going to tell us that I didn't actually specify the problem precisely enough to get an answer. We know dr dt. Okay, we want to know dA dt, so don't plug anything in there. That's going to be the answer. We know 2 pi. We know dr dt is 2 meters per second. Uh-oh, I can't actually solve this problem unless I actually know what the radius is at any given time. If you give me a circle and you don't tell me how big it is, but you tell me how fast the radius is changing, I can't actually tell you how much the area is changing because it's also proportional to the radius itself. Okay, so let's suppose, oops, we just forgot that what it really should say, something, often these problems in a book, for example, will say, find the rate of change in the area at the instant or when or something like that. There's often a little handy phrase, at the instant when, what was I going to say? At the instant when r is 30 meters. Okay. And you're going to want to look for that. Now, it's really important that I did not want to plug that in too early. It was really crucial that a and r are variables, and I take the derivative of variable quantities and get dr dt here. I don't want to plug in a 30 too early, but this is where I would plug in the 30 meters. Okay, and so I get the dA dt. My desired quantity is going to be 120 pi, about, I don't know, 400-ish meters squared per second. Does that make sense? Does the units make sense? Well, it's the rate of change of an area per time. So every second, roughly, we're predicting it's going to add another 120 pi, 350, 400, well, yeah, more like 400 square meters of illuminated area. So to go back to the sheet here, we differentiated the master equation, carefully using the chain rule, definitely. It's all a derivative with respect to t. And then before the plugging in values, we looked at, well, actually, I didn't do that in quite the right order. Here, there were no incompatibilities in the units. It wasn't like meters versus feet, second versus minutes, something like that. So, but be careful with the units. This one wasn't too bad for that. Plug in the values with the units. We didn't have to do a step, we'll in other problems where you have to go back to the master equation one more time to figure out some unknown quantities. This is a simple introductory example. So all we needed was that r equals 30 meters and we were good to go. And then we solve for the desired rate. We just sort of put all this together. So since this is a fairly simple example, we didn't have to do all the steps super carefully on this, but they're going to all apply in detail to a more complicated problem. So we've got our final answer that when the radius was increasing by 2 meters per second and the radius was 30 at that instant, then I get the rate of change here. So notice there can be, people find a tension here, I think. Wait, you're saying it's changing? You're saying it's constant? No, I'm saying it's changing, but then I just want to look at the snapshot, just the one frame of the movie, where r happened to be 30 meters. At that instant, given this rate of change of r, how fast was a changing? And we'll get a lot of practice with that idea.